Welcome everyone. This is the EasyPower Thursday webinar series. My name is Jim Chastain. I'm your host for today. And today's topic is a very interesting question. I think this is going to spark a lot of dialogue. And as we are in the habit of doing, we'd like to start off getting some information from the audience, if you would please, and do so by responding to the poll questions. And the first question is exactly that. Does OSHA require that an arc flash analysis be done? And this is kind of a preview for hopefully what you'll learn during the presentation. So no obligation, no liabilities, just strictly trying to get some feedback as we begin the dialogue. We will provide via email a certificate of attendance that most people use to support their extended credit requirements. And that's done automatically, so you don't need to do anything other than make sure your email address was correct when you registered. So it looks like we have a quorum. Let's see how people have responded here. All right, I like it. We've got a pretty good spread, and I'm in one of those categories. All right. The second question is a short circuit and coordination study required? And so let's see how you do on this one. Again, the OSHA requirements are a little bit overextending, and so sometimes it's even segmented by which market they're referring to. So it could be a conditional answer one way or the other. It looks like we got a quorum. Here's how folks have weighed in. This is a little bit more evenly split. But we still have a majority anyway. All right, thank you. Then the final question, if the short circuit and coordination were performed when the plant was constructed and commissioned, is that good enough? You got to admit these are pretty clever questions. Not that I'm bragging about it, but there are ones that kind of dance around the edges, and it's nice to have a discussion at a forum like this where we can participate in the pros and cons. All right, looks like we got a quorum. Here's what people have answered. Good. So now at this point, I'd like to hand the presentation over to our guest speaker, Mr. Lee Marshall, who is a frequent contributor to the EasyPower webinar series. Let me just take a second here to make him the presenter. Okay, Lee, you have controls.
Screen. Hello, everybody. Thanks for attending. It looks like we have a pretty good audience today. Very interesting results on the polls for sure, and we'll address those, I think, as we go. We will address those as we go. So our goal today is we want to provide useful information to assess and determine the best approach to minimize the risk of failure to your electrical infrastructure. And we'll talk about the consequences and all related to that. So by the time we're done, hopefully we'll be able to define what a short circuit and ground fault is. Some of you may be electrical engineers, so this is old hat stuff that you could teach, and some of you don't have a lot of experience with this electrical background, so we're going to go through a little bit of basics on that. We'll talk about time current curves and the importance of the coordination and short circuit study for OSHA requirements. And yes, it is an OSHA requirement. It's a little known section we're going to talk about. Compliance officers often don't know about that. I've been teaching electrical safety standards for a few years now, and I've been getting more and more compliance officers attending. I think it's kind of spread the word that there's stuff that they didn't know about. So. Okay, and we'll talk about the consequences of over-duty equipment. When I say, excuse me, when I say over-duty equipment, I'm talking about equipment that is not rated for the fault current that is available. So we'll talk about what that all means, and if the equipment's not coordinated, that's going to be a factor as well. So we'll talk about what this coordination and short circuit stuff is all about. So the standards that apply are OSHA and NFPA standards. Of course, then NFPA is the National Electric Code, NFPA 70, and from that came NFPA 70 in 1976. And so that's been around for a while, and that's the safety-related work practices that we follow. That's what OSHA based the Subpart S and Subpart K on back in the 80s. There's still parts of Subpart S are still from the 80s, and Subpart K is still from the 80s. So they're old standards. NFPA 70 is updated every 3 years. So that changes, and so it's a lot more in-depth and a lot more clear than what's in OSHA. But we're going to talk about both of them and how they interplay to each other. And then 70B is a good document. That's a maintenance guide, and that will help you to develop and to determine what you need for maintenance. There's checklists in there for how to do maintenance, and it works very well. The National Electric Safety Code is more of a medium voltage kind of a guideline, so that's a utility guideline or utility-like work. So if you have 4160 volts and higher in your facilities, that's where you're going to want to go to make sure you're in compliance with things that are not, again, in OSHA. There may be a lot more detail there. There is a lot more detail in the National Electric Safety Code than there is in OSHA, but that's also a guideline that was used for the electrical standards, more for the utility type of work. All right, I'm just going to get into a little bit of electrical basics, just so that everybody kind of is on the same page as we're talking about fault current and so forth. So we have atoms in everything in the world. We have atoms in the air and water. We have atoms in wire. We have atoms in glass. So they're all they all have the same kind of center part. The nucleus is made up of these positive protons and neutrons. And then we have these electrons that are flowing around the orbit, kind of orbiting these electrons. It's kind of like the Earth and the Moon with gravity, only it zooms around. It doesn't just slowly go around the orbit. And then they're held in place by what is called a valence. And so that's like the gravitational pull of the moon to hold the moon in place. Well, this valence holds those electrons in place. The type and strength of the valence varies from one material to another. So it's got a very strong valence that you would have in glass and things what we would call an insulator. It's got a very strong valence, and it's got a weak valence for things what we would call a conductor, like copper. And so if you've got a weak valence, then the electrons can flow out of the orbit pretty easily. So what happens with electricity is electromotive force will push these electrons out of the orbit, and so that's the voltage, that's the pressure, and the electrons are what causes things to heat up and things to light and all. It does all the work. And so if it's got a weak valence like copper wire, the voltage could be very, very small amount of voltage, and it can set these electrons free and get them flowing from one atom to another, so you can have electrons flowing. And that electrons flowing is amperage, and it's measured in amps, and that's the measure of how many electrons are flowing in a certain amount of time through a distance. So, and the strength of the valence that stops or impedes those electrons from exiting the orbit, the valence, is called resistance, and it's measured in ohms. So that's going to stop or impede the current from flowing. And so electrons in the glass, for example, have a very strong valence, so you could have high voltage, and it's still not going to push the electrons out of the orbit. So when we start talking about ratings of different pieces of electrical infrastructure, we're going to talk about parts that we want current to flow very well, which is the metal parts, and we want to have good contact, and parts we don't want current to flow, and that's the insulated parts, the plastics, the ceramics, the glass, that will prevent the current from flowing from one part to another. So as we start getting into fault current ratings and things like that, this is an important factor as to what kind of insulation levels you have between phases and between phase to ground. So that's kind of giving us a heads up here. Ohm's law is electromotive force, or E, which is voltage, is equal to intensity of current, or amps, times resistance measured in ohms. So if you look at this and just say we'll plug in 480 volts is equal to a certain amount of current times a certain amount of resistance. If we increase resistance, current goes down proportionally. So it's inversely proportional for current and resistance. So that's an important part of safety as we start talking about things. You know, when we want to have a very high resistance between our bodies in those parts to make sure current can't flow through our bodies, because it takes very little current to become a problem. The power formula is also an important formula because you notice I and E are inversely proportional. So the power is in watts or kilowatts or megawatts, and I is intensity of current, or amps, times voltage, electromotive force voltage. So these again are inversely proportional. So if I lower my voltage, I'm increasing my current. So if you've got a certain amount of load somewhere, and you've dropped from 12,000 volts at the power line down to 480 volts in your facility, the current goes up. So you have a lot higher current, and you also would have a higher fault current. And that's also something we're going to be considering as we talk about this. So that's a little bit on electrical basics, and then we'll just move on from there. So let's talk a little bit about fault current. Picture on the left shows a crane making contact with a power line. Incredible amount of energy in the fault current that occurs when this happens. This is a ground fault, but you can see it took the crane off the ground by about a foot. And then this is the very beginning of the bang, right when it made contact. I've got the whole series of pictures. Of course, the whole thing becomes engulfed in a big ball of fire, but this is just showing you what power can do. That on the picture on the right, this is what an over-dutied equipment would look like. So this is equipment that is not rated for the fault current, and so it fails, and it heats up, and of course then you could have injuries and outage time and a bunch of different things that could happen. So the same thing happens. So if I in a fault situation, what I'm doing is I'm taking a one phase and going to ground, or I'm going from one phase to another phase. And what I normally have in my electrical infrastructure is very high resistance between one phase to another, or one phase to ground. And we have to maintain that high resistance. That's part of doing maintenance, making sure the insulation is good between those parts and ground, or from phase to phase. So when that gets breached, so a screwdriver gets placed across two phases, and they're live phases. Now what we're doing is we're dropping resistance down to 0 ohms from a very high resistance, the way it's normally set up, to a very low resistance, and we're going to call it at 0 ohms. And so this is also called available bolted fault current. So what I'm doing by saying bolted fault current is meaning I'm bringing it down to 0 volts. So when I bring R down to 0, I, being inversely proportional, should go up proportionally. And then if it's at 0, then theoretically, I should be an infinite amount, because R is at 0. We don't have an infinite amount available, so it becomes all that is available from the system. So that short circuit or that ground fault is going to have the maximum amount of fault current that's available. And that may be 125,000 amps, it may be 10,000, it may be 2,000. Excuse me. So short circuit and a ground fault, we have, well, let's get into this arc flash for a second. So the arc flash that occurs, it occurs from a short circuit or a ground fault generally. Very often it's a ground fault that starts it. And then sometimes the air becomes ionized and it takes it to a three-phase fault. So the arc flash itself depends on the available bolted fault current, what that is, that level is. And then the clearing time, how long does it take for the breaker to open or the fuse to blow? That's going to have an impact on how big this arc flash is. As a matter of fact, the arc flash level is directly proportional to clearing time. So the longer it takes to clear, the bigger and badder and the worse the arc flash can become. So that's that's certainly something to consider. And then there's other issues related to impedance and distance that will have a factor on what the arc flash level is as well. From a ground fault and short circuit standpoint, a ground fault is from a grounded point, so this is part of the box that's grounded. And then this one is short circuit, so you got if you have something between these two differences in potential, when I say difference in potential, I'm talking about a voltage difference, then we've got a flash that it could occur. If you've got a short circuit, it's going to be the same thing. You'll have something across it, and it's going to cause a flash. And very often, if it's 480 or higher, it'll ionize the air, and then it'll create this plasma and turn into a three-phase fault, and then you have a real big mess on your hands. So we're going to talk about what causes these things and what we need to do to prevent them. So all breakers and all fuses, and I don't know if you can see me or not, but I have breaker and fuses in my hand. I've got a small breaker that is a 20 amp breaker, and it's rated for 120 volts, and it also has a fault current of 10,000 amps. So this is a Home Depot style breaker. That's the highest rating that you're going to get at Home Depot is 10,000 amps. So you don't want to use that on a system that is higher than 10,000 amps. So the point is if a maintenance person is going to put in a sub panel for a new test area or something, or a disconnect switch or something, so they've got a disconnect switch like this. This breaker goes in the disconnect switch, and if they've got a disconnect switch that's rated for 10,000 amps, and they're putting it into an industrial facility that's 65,000 amps available, that's going to be a problem. It's going to blow up instead of operate the way it's supposed to. So current limiting fuse, if the chart on the left is a note that comes off the 130.7C15A table in NFPA. And so this note was added in 2009 or 2015. So they actually finally put in what an average kind of clearing time is for different devices. So current limiting fuses can be a quarter of a cycle up to 2 cycles, depending on the type of current fuse that it is. There's different kinds of time current curves for fuses, as well as there are different time current curves for breakers. So this photo to the left are time current curves. So these will represent different breakers. So this may be a main breaker on the right, and then it may be the main distribution panel, then it may be the main breaker to a 480 volt panel, then a breaker feeding a motor, for example. So that will be the first one you want to trip, and so that's okay for up here. So let's break this down a little bit more. This section of the time current curve is your long time. So this is time in seconds. It starts at 0 and it goes up to 10,000 seconds. So this is a long time blowing. And so then you go into the time delay section, which is part of the it varies if you've got motor loads and things like that, so you want to make sure it's coordinated to whatever you're working with and coordinated with each other, but we'll talk about that in a second. And then there's short time pickup, and this gets into overload, and then short time, this should be short time pickup, and then this is short time delay down here. And then down at the bottom it says instantaneous area. That would be for short circuits and ground faults. So that's a very, very quick amount of time with a fairly high amount of current, depending on what your system is. So again, you can have equipment like this breaker right here. It's not a 10,000 amp breaker. At 240 volts, it's 200,000 amps. So it's got a very high rating. And you're not going to get this at Home Depot. You'd have to get this at an electrical supply store. So once you determine what your fault current available is, then you make sure your boxes and equipment and everything and breakers are all, and fuses are all rated for the available fault current. As a matter of fact, you probably want to exceed that by a 30 or 40% just to account for future changes in your load situation. So that's kind of in a nutshell what we're going to do. So these should be all coordinated. So the one feeding the equipment that you're working on that has a failure is the one that trips first. If you've got down in the bottom, you notice the first one tripping is going to be the orange one. The orange one is the main distribution panel. So the main distribution panel, if that goes, then there's a lot of load downstream, and I'm going to show you what that looks like. So these are the different panels. These are the four current curves that we just looked at. So we have a main switch that feeds the main distribution panel, and the main distribution panel breaker feeds the main breaker on this particular panel. Then we have a breaker that feeds the motor. We want this breaker to fail, to open, if we have a short circuit or a ground fault on the motor. And that would be just isolating the motor. But what happens in that time current curve that we talked about is the main distribution panel up here goes. So now all of these loads, so each panel with everything that's fed from those panels, they're all de-energized. So what if you go over to this panel and then there's a ventilation for a combustible dust area? Now you just created an explosive atmosphere because your system is not coordinated and the wrong breaker tripped. So it's more sensitive than the one that's than the other two. So either that's got to be changed up, but you have to make sure and coordinate it. So when I go back here, when I look at something like this is part of an arc flash study, which is a good benefit of doing an arc flash study because you do get a coordination and short circuit study at the same time. And there's time current curves usually in the study report. And if an engineer sees this, what he's going to do is he's going to drag this over to here with his mouse if it's adjustable. If it's not adjustable, he can't move it. And it's just so then he would make a recommendation to change the breaker to a different type or a different style with a different time current curve to make sure it's coordinated properly, and then you don't have those problems that you would normally have in this case. So this is the kind of thing that you have to be careful with coordination, is making sure that the breaker that has a fault is the breaker that's going to trip. You don't want a blow dryer in a bathroom killing the plant. It just doesn't, it's not a good thing. So there's, major outages like that can cause some major issues. Okay, so here's the OSHA stuff. So number one, so there was a question, does OSHA require that a short circuit study be done or an arc flash? It started off with an arc flash study. So OSHA 1910-132, this is subpart I, the personal protective equipment section. There's nothing in the personal protective equipment on arc flash, clothing, and that kind of thing. The only place that it's going to have that is in the utility standard. However, the electrical standard subpart S still refers to NFPA 70E. So they will, through general duty, sometimes refer to 70E, but there's also another section on electrical PP in 1910-335, which covers electrical protective equipment for the parts that are affected by the electrical hazard. It doesn't say what kind of hazard, and it doesn't say what parts of the body, so it pretty much covers the arc flash equipment as far as PPE is concerned. But this hazard assessment, 132, states that the employer shall shall assess the workplace to determine if hazards are present or are likely to be present, which necessitate the use of personal protective equipment. So employers have to do an assessment to determine the hazard and the protective measures that need to be done. So if it's an arc flash hazard that you're assessing, somehow you have to assess what that is. You can go by tables in NFPA 70E, or you go by labels from an engineering study. Engineering study is going to be a lot more accurate and give you a lot more detail, and it does the short circuit and coordination study requirement. So let's take a look at that. So this is 1910-303B4 and 303B5. These are part of subpart S, the electrical standards for general industry. It's not in construction, it's only in general industry, because in construction, they're just building it. There's no fault issues that they have to deal with. They're building it, they're going to energize it and walk away. But I believe there's still some wording in the construction standard about the impedance. But let's take a look at this. So first off, interrupting rating. Equipment intended to interrupt current or fault levels shall have an interrupting rating sufficient to the nominal voltage. So that's one thing that's on here. Nominal voltage 280, 240, 480, 600 volt class, depending on what it is, but most of the time it'll have a specific 120, 240 or 277, 480 kind of thing. So the nominal voltage and the current that is available at the line terminals of the equipment. That's the available fault current. And then equipment intended to interrupt current at other than fault levels shall have an interrupting rating at the nominal voltage sufficient for the current that must be interrupted. So that's the other one. So it's got a 20 amp rating that is for load, and that's other than the fault current. And then there's 10,000 amp on this breaker for fault current, and then there's the voltage rating. So all of these have to be part of the breaker. And of course, to determine what your current ratings are and making sure they're going to be sufficient for the current, you have to know what the fault current is. Hence, you do a short circuit study. And then circuit impedance and other characteristics. And these are titles that are misleading. One is interrupting rating, one is circuit and impedance and other characteristics. So you don't just look at these and say, geez, this means I have to do a short circuit and coordination study, but that's really what it comes down to. So the overcurrent protective devices, the total impedance, the component short circuit current ratings, and other characteristics that the circuit to be protected shall be selected and coordinated to permit the circuit protective device used to clear a fault and to do so without occurrence of extensive damage to the electrical components of the equipment. So that's why it's got to be rated for the fault current, because otherwise it's going to blow up like the panel I showed you. It's going to be overdutied. It's not going to be able to handle that level of fault current, and it's going to blow up. This fault shall be assumed to be either between two or more circuit conductors phase to phase, or between any circuit conductor and the grounding conductor or enclosed metal raceway. So the box, whatever's grounded, and that 2-1 phase would be a ground fault. So this is pretty clear that a short circuit study and a coordination study is required. Now, let's get back to the question that was on the polls about what about when I do it initially, is that enough? So there's nothing in OSHA that says this coordination and short circuit study has to be done periodically or every 5 years. NFPA 70E gives you the guidelines, so there's no guidelines in here as how often this is done. OSHA would go to the NFPA standard as a guideline and with general duty to say it hasn't been done within 5 years. But I don't even know that they would go there. They would just say this is not adequate information because it's been too long since it's been done. So this is one of the reasons why we're getting so many arc flash incidences every year, is because people have done their arc flashes. Let's take a plant that came into existence in 1964. They knew what kind of load they were going to have based on the equipment that they were installing, so they sized up the transformer, sized up the main switchgear, and all the panels for the facility and all that were designed. So they went by the load for overcurrent protection, and then they did an assessment based on the transformer and the available fault current from the utility. They made an assessment of what their fault current and their so they could do a short circuit and ground coordination study of the plant, which is required upon completion. So they've got that all done. Probably engineering has had that done before it's even built and before you even order the parts, you know, the transformers and the equipment. So then you know what you need to have. Like this box that I'm holding in my hand has got a 10,000 amp rating. That's not going to work very well in an industrial setting. So you'd want to make sure that that's working fine. The problem is that was in 1964. If the study has not been done since 1964, the fault current available from the utility is way different than it was in 1964. The loads have gone up, there's more generation, there's more transmission lines, more substations. It's all shifted, and now the fault current is much higher on the high side, which is going to have an impact on the low side as well. So now the equipment that was rated for the fault current is no longer rated for the fault current, and instead of holding up and tripping the breaker, it blows up. And now if somebody's there and they're not planning on having anything happen and it happens to blow up and they weren't fully protected with the level of arc flash protection that they need, it becomes a problem. And that's where the tort cases come into play, and we'll talk about those at the end of the program today. So a little on arc flash. So we have to know how far out this ball of fire is going to go, and that ball of fire is going to be directly proportional to clearing time of the protective device, depending on what that is. And of course, the level, also the heat and pressure has an impact. The available fault current has an impact on that. So it's 35,000 degrees. In a box, it's going to be a little worse, about 10 times greater than it would be in open air, because of the directional type of a system. Like a cannon, it's going to go in one direction. And so we talked about the severity depending on what the level is, and it's not an arc flash class, so I'm not going to get into the calories and so forth. Copper vapors expand 67,000 times. Molten metal comes out 700 miles an hour. Pressure waves 2,100 pounds. All this is, so if it's a ball of fire like this, you still have all of those things happening. So the metal is not going to stop. That's going to keep on going out. But the actual ball of fire at that 35,000 degrees will have a level of that will go out to a certain point based on the time current curve of the breaker and the fault current. And then you have sound waves. So all of these things are dependent on those the breakers being not over-dutied and being properly coordinated. So at arc flash level, so this was an arc flash hazard that was done, or an assessment that was done for a plant that had old switchgear, and then this new company bought the plant and they decided to replace all the switchgear and get smaller switchgear because they didn't need the 4,000 amp switchgear that was there. So they put in 1,500 amp switchgear and all new panels going downstream. They thought it would be much lower arc flash level because it's a much smaller switchgear. Thing is, the transformer outside is still 5,000 kVA transformer. So, and it's still from the 60s. So it's got low impedance and causes high arc flash levels. So in this case, we have 96 calories at this point. If an arc flash were to occur, it would be catastrophic and it would cause a problem. Downstream, it's going to be a little less because it's protected by the main, but you have to protect people for the whole switchgear for the highest level. So 96 is what you need. And of course, we only have a 40-calorie arc flash suit, so it's not enough. So once they changed the transformer out, it went down to 28 calories, and they got a 1,500 kVA transformer instead of 5,000 kVA, and the impedance was much higher. Going from one of these main distribution panel breakers to a bus duct, we're down to 18.6 calories. So a suit is enough. I go up into my aerial lift and change out a fuse. I got to be in a suit. Of course, the suit you're going to have to be in if it's a lift and it's your policy to have fall protection on, then you'll need to have fall protection on. And if it's on the outside, you'll need to have fall protection that's arc rated. So you're going to have to be careful about making sure you have the right equipment for that. And people think, well, I'm only changing out a 15 amp fuse. Well, your bus plug is on the bus duct side, and that's going to be this 18.6 calories. So that means every one of these cabinets have that calorie rating inside. So even though it's a 15 amp fuse, it's not our small time arc flash hazard on the line side or the bus side of that fuse. It's going to be still high. So this is going to feed a breaker. We're down to 33-inch arc flash boundary, 7.6 calories. So it's getting down there. Now all of these are going to go down once they change out that transformer. Everything downstream goes down as well. But a balaclava shield and a hard hat. And then from downstream from there, we've got fuses. And downstream from the fuses, it's going to be extremely low because fuses are fast. And the good thing about fuses as well is they don't require maintenance. They're going to be operating at a very low level or opening up. So downstream so we're still in in this panel, we're still in a shield. Downstream, we are into the control cabinet area, and it's at a very low level, 0.5 calories. So with cotton clothing and plastic rim glasses, of course, arc fleet, rubber gloves are rated for arc flash and shock, so that's covering up close arc flash. That's another thing that people don't think about. So we got 0.5 calories, which is less than 1.2, so you don't need a shield, but doesn't mean you don't want protection for your fingers, because at 2 inches away it could be 5 or 6 calories. That'll certainly burn your skin to a second-degree burn. So rubber gloves with leather protectors are both shock and arc flash protection. So if you do a study, then you come up with tables like this, and the table shows the bus name, the protective device that's protecting whatever it is you're working on, and then it has the bus voltage, the fault current, the available fault current is on there. So let's take a look at some of these. All of these are 2, all the way down, 2-second clearing time. And what this means, they probably had either over-duty breakers or something where there's the default that you can use, which is a 2-second rule. And that allows, basically, it's enough time for you to get away and run away from the flash in 2 seconds. So that if you went with what would be reasonably staying energized for 5 seconds or 8 seconds, then it would be such an unreasonable high number that it would not make any sense. So we use 2 seconds as a rule and the default in the software, which is based on IEEE 1584 standards. You'll notice where there's lower levels, so 0.14, this is from this tap, it's at 2.5 calories, so it's going to show a much lower arc flash level versus the 2-second ones that are 25 and 26 calories. And then the arc flash boundary, of course, is going to reflect that time element as well. So this is all data that's on your arc flash information that's available on the arc flash study. Okay, so let's take a look at a couple of scenarios. Qualified person has to assess the risk, and so we've got a 1964 switchgear that's got a ATS that we're connected to it, and we're going to work on the ATS. So this is both identical equipment. They're both 1600 amps. They're both 480 volts. So they're identical. The only thing that's different is this one's 1964 and this one's 2004. So at first glance, you think, I'd rather work on the 2004 switchgear. It's going to probably be safer than the 64 switchgear. Well, that at first glance may be the case, but then you start looking into it a little bit deeper, and you find out that this one has an arc flash label and tells you what it is. That's one good thing. And then it also has maintenance labels, and the maintenance labels are one after another, so they're kind of stacked up onto the switchgear, so you know it's been maintained on a pretty regular basis. This one, 2004 switchgear, there's no stickers. So you contact the facility manager and you say, how long since you did maintenance on this? Well, Lee, we haven't been very good about that. I said, well, give me a time frame, you know, just a general idea. Well, I don't think we ever have. So it's now been 18 years since that's been maintained. Manufacturer recommends 5-year maintenance plan. So you have a main breaker that requires load testing, and that's not been done in 18 years. So now, so there's no arc flash level that we know of, and there's a breaker that we don't know if it's going to trip in the time current curve it's supposed to. This one has fuses. It's got a switch, but it's got fuses. The fuses don't require maintenance. Those are going to be protective, and it's been maintained. So now I just shifted. I'm now saying I'd much rather work in the 1964 switchgear than I would in the 2004 switchgear. So this is what risk assessment is all about, and this is taking a look at things from a standpoint of equipment. All equipment has to be labeled and listed for the use. So I showed you breakers and boxes and stuff. There's 3 ratings: load ratings, fault current ratings, and voltage ratings. Has to be labeled and listed. Boxes, breakers, splices, like this is a UL listed splice, tells you the size of the wire that can be used. This is has a labeling and listing, but it's labeled and listed for a hose clamp. It's not anything to do with electrical rating. So the next thing people are going to do is wrap this up with about 15 layers of black tape, which is also not listed to protect against shock from live parts. It's not designed to go onto metal. And if you look at the labeling and listing of black tape, it's a secondary protection, not a primary protection. Okay, so we talked about the coordination and short circuit study. So this is a breaker that was rated for 35,000 amps, 480 volt, 600 amp breaker. And so it's rated for 35,000 amps, and it was a 65,000 amp fault. So it didn't hold up, it blew up. Nobody got hurt in it. It probably looked something like this when it happened. It blew the door off and so forth, but nobody was there when it happened, so thank goodness nobody got hurt. So if this was rated 75 or 85 or 100 amps, 100,000 amps, it would have not have blown up. It would have just tripped the breaker and life goes on. You fix the problem, reset the breaker, and you're good to go. So that's the problem with overduty. This is an overduty breaker that's a 10,000 amp breaker. So like the single phase breaker that's in your house. And this is a 35,000 amp fault. So this was in a facility that they did put a sub panel in. They used the sub panel from Home Depot. It looks fine, trips and opens up. You could turn it on and everything came on fine. But when it came time to handle a fault, the fault current was too high and it blew it up. So now you've got more outage time, and hopefully nobody was around to get hurt on that one. So these are called over-duty breakers. They're not going to handle the available fault current. So as far as the consequences from a fault, these are just some of the things that can happen. Service outage, production loss. That can amount to quite a bit of losses, depending on what the outage is. You may interrupt critical loads if you're not coordinated, that we're talked about. So you're taking out a power of a lot of places that they shouldn't have been without power. And now those critical loads, I mean, hopefully critical loads like that are on a transfer switch with a generator. So if the power does go out, it provides power for those critical loads, ventilation or other kinds of equipment that would require emergency use of equipment and so forth. Extensive equipment damage. So sometimes, especially if it's main switchgear, you don't just get that main switchgear overnight. It's going to take weeks of design and to make sure that it's going to fit, and it may have to be built. So it could be weeks of outage time. Personal injury and death, we're going to show a case in a second on that, and hopefully that doesn't happen. But because of your miscoordination or not having things rated for short circuit, it could cause these major issues if somebody happened to be in those areas. And then fire damage. If there's combustibles in the area when you have this big arc flash event, then things catch on fire, and now you've got this catastrophic fire that takes your facilities down. As far as the injuries and so forth, this is from the Industrial Safety and Hygiene magazine a couple of years back. So there's an average of 7,000 burns a year. 2,000 of those are hospitalizations, and there's about 400 fatalities. That should be going down. It's not going down because the available fault current and clearing time and coordination of circuits is not being done, and that's what the problem is. So here's a case that happened in California, settled for $13.9 million. If you want some ammunition of why we need to do it, this is sometimes what it takes with upper management to understand how serious this is. So let me just read through this. An industrial software technician who suffered serious burns in a plasma explosion, so it's an arc flash, when a high voltage circuit breaker at an asphalt plant shorted out, had secured a $13.9 million settlement in his suit against the plant's owner and operator. And then down here it said the plaintiff's lawyers allege that the accident was a result of a failure to perform routine maintenance. Part of that is doing a short circuit and coordination study. That's part of 70B. That's part of the arc flash level. As far as the timing, 5 years is a guideline that's used by NFPA and the IEEE 1584 software. That's a guideline that OSHA would look for and possibly cite using the general duty clause. But they would probably go into 303B5 and cite you for not doing it. And then you would have to, when you're fighting this kind of thing, your lawyers would have to say, okay, well, there's nothing that says it's 5 years. Well, good luck with that kind of an argument. So that they didn't win that argument. In this case, it's $13.9 million that was paid for in this case. Okay, so hopefully we have a better idea of what the risk is, or or how to minimize the risk of failure to our structure. It is an important part of what we do and what we need to do. If you've done an arc flash study and you do it every 5 years, you're doing a coordination and short circuit study. One thing you got to be careful of when you get an arc flash study done, it's not done, labeled, and you're all set, you're good to go. You got to read the study, because the engineer will put recommendations that this is over duty, this is over duty, there's an NEC violation, and they're now in writing to you to tell you what the hazards are, and you need to fix those. And so if you don't fix those, then you're still going to be on the hook. Just doing an arc flash study is not enough. Make sure facilities people understand if there's some recommendations that need to be done, then they need to be done, and that's pretty important. So hopefully we define the short circuit and ground fault, what they are. We talked about the purpose of time current curves for both coordination and short circuit, for tripping and so forth. And then we talked about the coordination and short circuit study with OSHA, and got into some of the consequences of having overduty equipment that is not coordinated. Okay, and that's the presentation for today. Or do we have any questions on anything?
Well, I'm looking right now. We've got some congratulations on a good webinar. Leah, appreciate the great job. We will, I don't see anything else coming in right now. We will forward on, there's more people appreciating it.
Oh,
We will
good.
forward any questions that come in after we sign off and answer those via email.
That would be fine.
Here's a question. Let me jump back in there. Okay. So this is from Joseph. Is what of, or if the voltage rating of the switchgear is lower, but the breaker is rated properly?
No,
So,
I understand that. So you have an example like a 208 rated panel that's installed in a 480 volt system with 480 volt breakers. So the breakers, as long as they're available, they're tied and rated for the available fault current, aren't going to fail themselves, but the panel may fail, because what's happening is the insulation between each phase is going to be less on a 208 volt panel than it would be on a 480 volt panel. So generally, just energizing it doesn't cause it to blow up. But there's if you have any kind of, it's gonna be treated. You'll want to treat it just like an overduty panel, and replace that as soon as you can, because the insulation between phases and phase to ground, well, mostly phase to phase, is going to be different. Well, phase to ground too.
here's a question. Says you, the presenter, seemed to favor fuse-based equipment over circuit breaker-based equipment. Is that true, or?
Yes, that's a good comment, and I definitely do. Mostly because fuses are always good, and then fuses are almost always faster. So because they're faster, the arc flash is going to be less. So if I help a company set up a test area, for example, I'm definitely going to fuse disconnect switches with receptacles that they plug in their test leads to and so forth, because that's going to bring down arc flash levels to very low levels, probably to a point where shields and all that are not required, because it's so fast and it's reliable.
This question, it's open for discussion. It is, what is the maximum incident energy if the range is not definite, such as level 2 is greater than 12 for PPE requirements? I don't quite understand that.
Yeah, I'm read that one more time.
What is the maximum incident energy if the range is not definite? In other words, such as level 2 is greater than 12 for PPE requirements. I think he's saying, I think he's mixing the lookup table with the instant energy levels.
Yeah, I mean, so you got tables and labels. Tables by using NFPA tables, category system, and labels is engineering system, and then you just have to match up with whatever the calorie rating is of that incident energy for the engineered stuff. On the tables, you have table category 1 up to, you got to wear a minimum of 4 calories and have a shield. Category 2 is a minimum of 8 calories and have a shield and a balaclava. And then category 3 and 4 are essentially a suit. Now, some companies have 25 calorie suits, but not very many. Most people just have 40 calorie suits. So it's either one of those 3 that you would determine to be your arc flash level that you need. So here's the problem with using the tables, and I may be drifting a little off from the answer. If you use the tables as a guideline, think of that example where it was 96 calories. So according to the table, if you weren't careful and diligent about determining your fault current and clearing time, which is part of using the tables, you have to know those, then you are very well not going to be fully protected, because you would put a suit on saying it's a 480 volt switch gear, so it says I got to wear category 4 gear, but category 4 is not enough. It's actually 96 calories, not 40. So if you don't do that assessment to determine your fault current and clearing time, that's another reason to do this study. But if you're going to do that level of study to use the tables, you might as well do an engineering study, because once you get the data for the short circuit and coordination study, you got all the data you need for the arc flash study. So it's just, I mean, that's just the better way to go, is just get an arc flash study done, then you've got it all done. And it helps give you ammunition of why the arc flash study needs to be done. It's also OSHA compliance with coordination and short circuit. I know I drifted there. I'm sorry about that.
No, it was a good discussion. There is another question here from Harold, and he's saying, does it mean if I want to correct an issue with the number of main lug only panels in line, I can interrupt the feeder to those panels with a correctly rated fuse disconnect instead of a main breaker, which cannot be mounted after the installation?
Yes, you certainly can. I mean, sometimes main lug panels come off of main distribution panels. I don't I don't have any big preference. I mean, the good thing about having a main breaker in a panel is that it lowers down the arc flash level on the bus work. The feed coming in is still going to be the same level as it would be whether it's a main disconnect switch or a main lug. You certainly can do that for sure.
The next question, can we say fuses are better also in terms of coordination comparing to switches?
From a coordination standpoint, coordination's coordination. So you're going to look at the time current curves of both breakers and fuses and make sure they coordinate together. So if your fuses are upstream are quicker than the breakers downstream, if you had that kind of scenario, then you'd have to change your fuses to make sure that they're slower blow fuses to coordinate, and that so that breaker downstream would still be faster. That generally, well, it happens. I mean, there's certainly places where they put sub panels onto panels that are fed by fused disconnects on switchgear, especially older kind of switchgear. So that can happen. But it all comes down to making sure it's the coordinated properly. So you want to change the time current curve of the fuse to match up and coordinate with your system.
Here's another question that comes up frequently. Does a safety switch or do safety switches required to have arc flash labels?
Safety switches.
I'm thinking a fuse disconnect or a disconnect for a motor.
Yeah, so no, not necessarily. Generally, arc flash study is going to go down to the panel level. Personally, I prefer to do a study right down to the disconnect level if they are larger disconnects. 100 amp, maybe even 60 amp, but usually 100 amp, 200 amp, 300 amp, 400 amp switchgear disconnect switches should have labels. So if you are sure the arc flash level's at very low levels, so if you have a panel at less than 1.2 calories, and the likelihood of having a higher level is unlikely unless you have a large motor load or things like that, but or long runs of wire. But most of the time it's going to be downstream will be at that same low level or lower because you're now 2 levels down of protection levels down beyond the low level that you already have. And when you have that, we will generically label low disconnect switches that are smaller disconnect switches. Just put a generic label saying there's no arc flash hazard essentially that you have to worry about, so you don't have to put on all this gear to troubleshoot and de-energize and test de-energize and stuff like that.
The next question is, you might want to mention that you can't coordinate breakers with instantaneous pickup if the fault current exceeds the pickup of the upstream device unless you use zone interlocking. Reducing the resistance of pickup of the feeder won't solve the problem.
Good point. I think he covered it.
Yeah, I think it's a good statement.
Yes, absolutely.
When we talk about fault in the upstream and to see the same amount of fault, how does the fault going to the system talk about buses in modeling? That confuses me. When we talk about fault and the upstream see this, if the fault in the upstream sees the same amount of fault, how does the fault going to a system, why do we talk about buses in modeling?
Well, I mean, it all depends on protection of the bus. So if you've got you've got a protection, either breaker or fuse for the bus, and then you go downstream from that. I mean, so you're looking at upstream, but then you look at protection levels that are protecting the bus, and that's going to bring it down to a lower level. And then you go downstream from that bus to different breakers or fuses, and that's going to bring it down from those levels. I don't know if I'm quite capturing.
Let me interject something. If I'm looking at the question right, when we're modeling, we talk about buses because the impedance has to be measured between 2 points, and so it's easier to measure between buses to know what the protection level needs to be to protect that particular bus. So it's something that's in line with the cable, but it's calculated based upon what the bus voltage and current's going to see. Don't know if that helps.
And the protection level of whatever's on the bus. Yeah, that sounds good.
Shaid is saying fuse-based equivalent is live front. How is it better? Fuse-based.
That is live front. Well, I know what he's saying. So the fuse at the fuse itself is not better. It's downstream from the fuse. So I think that's what he's saying.
Yeah.
And that would be absolutely true. And that's a good point. If I go into a fuse disconnect switch, fuse doesn't help me there. If you had a load side fault, that they will help. They'll trip quickly. But on the line side of the fuse, it doesn't do anything for you. So it's still the same hazardous level as whatever's upstream.
Yeah, as far as opening that disconnect.
Upstream is very, very low, then it's going to probably still be low unless it's a long ways away.
Right. And then looks at the last question, and this another question that comes up frequently: are arc flash labels for equipment controllers required for VFDs?
That's a really good question, and that one's a tough one too, because you could have various results at various parts of the operation, and so you end up labeling for worst case scenario, and sometimes it ends up being at high levels because of the clearing time issue with the VFDs, and so that a little more gets a little more complex, and so that's something that
case by case.
Right.
One last question: is adding a disconnect switch with a Type J fuse to an overdutied equipment solve it? Is adding a disconnect switch with Type J fuse to an overdutied equipment controller solve it?
So It probably could, but I don't know if you would be coordinated with the system, and that might be the problem. So, some of the breakers, that may be too fast for some of the breakers. So you're bringing down the arc flash level, but you may not be coordinated any longer with the system downstream. So you have to look at that and play around with it to see if you can coordinate that.
I think that's the end of our questions.
Okay.
Thank you again for a good presentation.
You're welcome.
Just for the audience's sake, the presentation was recorded and we will be posting it to the website by early next week. Thank you all for attending. Have a good day.
Thank you.